Hi everyone. So in the last few videos, we've been looking at different methods of evaluating limits, and specifically the last two videos have focused on using algebraic simplification in order to evaluate a limit. So in this video, we're going to see one last method, and this is a method that you will use basically in certain circumstances when algebraic simplification just can't really be done. So I'll start by showing you an example of what type of function you might use this for. So this method is going to be called the Squeeze Theorem. So I'll give you an example first, and then we'll get into what the theorem is, and then do another couple examples. So let's say that you are asked to evaluate the limit. The limit as x approaches 0 of x squared times sine of 1 over x. So let's try to think about the methods that we have so far. So the first thing you always want to try to do, if possible, is to plug in the number, right? So if you have a function that is not a piecewise function, then you can plug in the number as long as the function is defined at that number. So if we try to plug in 0, we would get 0 for the x squared part, but then we would have sine of 1 over 0, and that is undefined, right? So we cannot just plug in x equals 0, because basically we would get this part that would be sine of 1 over 0, and that would be undefined. Because 1 over 0 is undefined, you also can't take sine of 1 over 0. So the next method that we have been talking about, other than just plugging the number in, is, okay, well then maybe let's do some algebraic simplification, and maybe then we can plug in the number. But in this case, there's really no simplification you can do, right? Because we have an x squared and we have an x, but they're not even in the same place, right? One of them is outside of the sign and one of them is inside of the sign. So there's just no way to use algebraic simplification. So we cannot simplify algebraically. So what we're going to do instead is this thing that's called the Squeeze Theorem. And basically the idea behind the Squeeze Theorem is that we're going to find two other functions that are simpler that we actually can kind of evaluate, that this function is in between. And we're going to use those two functions as kind of comparisons to help us figure out what this function's limit is. So I'll write that down in words, and then we'll see exactly how it works in a moment. So instead, we will compare, and I'm going to call it g of x. So g of x is equal to x squared times sine of 1 over x. So that's the function that we're trying to take the limit of. We'll compare this function to other simpler functions. And so these other functions we'll find, those will be ones where we actually can evaluate the limit directly. And then from there, we'll be able to conclude what the limit is. So I'll just finish this sentence by saying, and we'll use those functions to evaluate this limit. And we'll see what I mean by that in a second. Okay, so let me show you what the Squeeze Theorem says, and then we'll see how we can apply it to that example. So basically, the Squeeze Theorem is called the Squeeze Theorem because the idea is that you are going to find two other functions that kind of squeeze the function that you're focusing on. And I'll show you, I think, a picture will help you really understand why it's called the Squeeze Theorem. So first of all, actually, maybe let me just talk for a second about the word theorem, because maybe you've seen that word thrown around with like Pythagorean theorem, whatnot, but maybe you aren't exactly sure what it means. So a theorem is basically a fact. It's a mathematical fact. It's something that you can, usually it will have kind of a first part and a second part. And basically, if the first part is true, then you can conclude that the second part is true. So oftentimes when you see a theorem, it will have this structure where it's like, if this, then that. And so when you apply this theorem, you have to kind of first focus on the if part and make sure that all of that stuff is true. And then once you've figured out that that stuff is true, then you can conclude what you're trying to conclude. So the Squeeze theorem says, if you have a function, so let's say you're trying to find the limit as x approaches some number of a function g of x. If you can find another function f of x that is less than or equal to g of x, and then another function h of x that is greater than or equal to h of x. And this inequality doesn't always have to be true. It just has to be true when x is close to the number where you're taking the limit. So I'm going to say when x is close to a. So if that's true, so if you have your function and you can find these other two functions to kind of squeeze it between, if additionally the limit as x approaches a of the bottom function is the same as the limit as x approaches a of the top function. So basically, if this top and bottom function agree at the limit, and let's say that that limit is equal to some number L, then you can conclude that the limit as x approaches a of g of x is also equal to L. So let me draw a picture to kind of help explain this. So basically what we're saying here is if you have a function g of x, so say my function looks something like this. I'll just make it some crazy function. So this is g of x. And then you have another function that is above it. So maybe let's make this one be the top function, or oops, that's reversed. I want to be consistent with my color here. So the top function should be in red, right? So if this function is always above, sorry, having some pen difficulties here. So if this function is above, and then this other function is below, well, then that means that the blue function, the original function g of x, is getting squeezed, or another word that people will sometimes use for this theorem is they'll call it the sandwich theorem, because that middle function is getting kind of sandwiched between them. And so if you're taking the limit, let's say with this picture, you're taking the limit as x approaches 0, well, if the red function is going towards a certain height and the green function is also going towards that height, and then the blue function is stuck in the middle of them, well, of course, it's going to go to that same value. And so what we'll see is that you can use this because this function g of x, maybe this function g of x isn't actually defined at a, but the top and the bottom function are. And so you can kind of use them almost as like stand-ins or like aliases for this middle function and use those two to figure out what the limit is. Okay, so let's jump back into an example, and we're going to do the example that I had written earlier. So let's say that we're trying to find the limit as x approaches 0, again, of x squared times sine of 1 over x. So let's call that function g of x. So g of x is equal to x squared times sine of 1 over x. So what is our goal in this problem? Our goal is to find two functions, and specifically we can call those functions f of x and h of x, such that g of x is in between them, right? So such that f of x is less than or equal to g of x is less than or equal to h of x. And it doesn't need to always be true. It just needs to be true when we're close to x is equal to 0. Let me say it that way, when x is close to 0. Okay, so how are we going to do this? basically, we want to take our function x squared times sine of 1 over x, and I want to focus first on the sine of 1 over x part. So this is a really important fact to know, and this will come up like all the time when you're doing the squeeze theorem, is anytime you have sine of anything, it doesn't matter what is inside these parentheses. So you could have sine of x, you could have sine of 1 over x, you could have sine of x squared plus 5, you could have sine of negative 2x squared minus 7x plus 1. Sine of anything is always between negative 1 and 1, right? That's just how sine functions work. As long as you're not multiplying it by a number, so like 2 times sine of x, well, then that would change. But if you just have sine of something, there's no possible way that that is ever going to give you anything bigger than 1 or smaller than negative 1. And same thing, by the way, for cosine. So we'll do another example in a little bit with cosine, but you could say the same thing. You could say cosine of anything is always between negative 1 and 1. So how does this help us? Well, in this case, we can say that sine of 1 over x is between negative 1 and 1. So we're not quite there yet, right? Because that's not what we want. We don't want to figure out what sine of 1 over x is between. We need to figure out what x squared times sine of 1 over x is in between. And actually, there's one more thing I should add here, which is that this statement that I just wrote down is true for all x not equal to 0. Right? Because when x actually equals 0, this statement that I just wrote down isn't true, because sine of 1 over 0 is undefined. So you can't say undefined is between negative 1 and 1. That just doesn't make sense. So this statement we wrote down is only true when x is not equal to 0. But that's okay, because all we need to figure out is 2 functions on the top and the bottom when x is close to 0, not when x actually equals 0. So from here, if we're trying to figure out what is x squared times sine of 1 over x between, what we can do is we can just take this whole equation or this whole inequality and multiply everything by x squared. So what will that give us? Well, if we multiply negative 1 times x squared, maybe let me write that down here. We're going to multiply everything in this inequality by x squared. And why are you allowed to do that? Well, anytime you have an equation or an inequality, you can multiply both sides by something. The one thing you would need to be careful about is that when you have an inequality, if you multiply or divide by a negative number, that will flip the sign of the direction of these less than or equal to or greater than equal to symbols. But x squared is always positive, right? So we don't need to worry about that. The direction is not going to change. And so if we multiply everything by x squared, we end up with negative x squared is less than or equal to x squared times sine of 1 over x is less than or equal to positive x squared. So we just found our top and bottom functions to squeeze x squared times sine of 1 over x. So what are those 2 functions? They're f of x is equal to negative x squared, and h of x is equal to positive x squared, right? That's our top and our bottom function. So what do we have to do next? So the first step is, again, figuring out what is the top and the bottom function. What are the functions that you can squeeze your function between? So we figured that out. The next thing we need to do is we need to take a limit, right? We need to determine whether the limit of the top and bottom function agree with each other, right? So that's going back up to the squeeze theorem. We did this part, right? This part we can check off. We found functions above and below our function. But the second part is we need to guarantee that the top and bottom function have the same limit. And if we can do that, then we can conclude what our final answer is of the function that we're actually taking the limit of. So next thing we need to do is we need to find the limit as x approaches 0 of negative x squared. And then we're also going to take the limit as x approaches 0 of positive x squared. So these two functions are a lot easier to deal with, right? We actually can just plug in 0 because in this case, there's nothing undefined, right? You can just plug 0 in. So what's the limit as x approaches 0 of negative x squared? It's just 0. And what's the limit as x approaches 0 of positive x squared? That's also 0. So that's good. That means that the top and the bottom limit agree. And from there, we can conclude that the limit as x approaches 0 of the middle function, x squared times sine of 1 over x, is also equal to 0. So I know that this is probably feels very different from other math you've done in the past. You might feel like we did a lot of work for kind of like nothing in a way. But one thing that I like to think about calculus is that I think of calculus as kind of a stepping stone towards upper level math classes. And once you get to the math classes that are, like basically anything past calculus, there's a lot of problems where it's not so much about calculating something or, evaluating something or graphing something. It's more about proving that something is true. And so it's about understanding logic and being able to kind of present steps in a logical way. And that's really what this kind of a problem is. So you might even be able to tell, maybe you already know, oh, okay, the answer is going to be 0, but the point isn't just saying, oh, the answer is 0. The point is really being able to provide the logical steps to support that. And so just one more time, just because students oftentimes struggle on these problems, I just want to make it really clear what I expect you to show on a problem like this. So what I would expect you to show is I would expect you to, first of all, you would need to tell me what are the two functions that our function is in between. That's the first step that you definitely need. And you should also show where that came from. So where did we get this equation I just circled in orange from? It came from this, right? It came from this beginning idea. And usually with these squeeze theorem problems, that's going to be the first step. It's going to be saying, okay, sine or cosine of something is between -1 and 1. Once you've established what your top and bottom function are and that you have this function that's between them, then you need to explicitly say what is the limit of the bottom function, what's the limit of the top function. If you get the same thing in both of those, then you can conclude that the limit of the middle function is that same number. So I need to see all those steps in a problem like this. I need to see you saying what are the top and bottom functions and then also taking the limits of those top and bottom functions. The most common mistake I see students make is they'll write this down and then they'll jump to something like this. They'll just say, okay, well, that means I can just plug in 0. And then they'll say, okay, 0 is less than or equal to x squared times sine of 1 over x is less than or equal to 0. And that just doesn't really make sense because if you're plugging in 0 for x, you should be plugging it in everywhere, but you can't actually plug 0 in for x into this middle function because it's undefined. So there's really no way to answer this question without using limits. So I really want to make sure that I see this step with the actual limits written out. Okay, so I want to show you what the graphs of these look like, just to give you one kind of more visual of what's going on, and then we'll do another example. So here I have graphed in, and let me see, I'm not sure. Okay, yeah, I'll put it in this mode. So right now, let me get rid of these for a second. So x squared times sine of 1 over x is this function here. So it's kind of an interesting function. It on the left and the right hand side, it just kind of like goes off, but in the middle, it starts to look kind of like a sine graph, right? It has this like wiggly shape. So that's the function we are trying to find the limit of. And the limit does not exist, or sorry, not the limit does not exist, but the function's actually undefined at 0. So even though it's all squiggly here, if you actually were to try to hit a point at 0, it would tell you it was undefined. And then we found that the function that was always above was x squared, and the function that was always below was negative x squared. So you can really see that this blue function is truly sandwiched between or squeezed between this top and bottom function. And that continues as you get closer and closer to 0. And so basically what we did is we used the fact that this red function goes to 0 and this green function also goes to 0. And so even though this blue function is not defined at 0, its limit must also be 0 because its graph is basically being forced, it's being squeezed to also hit at a level of 0. Okay, so we're going to do another example. So this example, we're going to do the limit as x approaches 1 of x minus 1 squared times cosine of 1 over x minus 1 plus 5x. So there's a couple things different about this from the previous one. So maybe, yeah, I should say a few things. So it's cosine instead of sine, but that's not really going to make a difference because cosine is also bounded between -1 and 1. So the general procedure will be pretty similar to the last one. Another thing that's different is instead of just x squared, we have x minus 1 squared, and here we have x minus 1. But that doesn't matter because remember that cosine of anything is between -1 and 1. So it doesn't matter if we have 1 over x or 1 over x minus 1, regardless of what is inside those parentheses, we'll be able to say the same thing. The main thing that I think is most importantly different here is that we have this plus 5x. And so in order to be able to use the same approach that we did in the previous question, before we get started with the squeeze theorem, we can use one of the rules that we talked about in a previous video. So we talked about this rule in another video that said that if you're taking the limit as x approaches a of a sum of two functions, f of x plus g of x, instead of taking the limit of that sum of the two functions, you can take the limit of each function individually and add the results up. And so that tells us that for this problem, instead of writing our limit as it is up here, we can rewrite it as the limit as x approaches 1 of x minus 1 squared times cosine of 1 over x minus 1 plus the limit as x approaches 1 of 5x. So we can take those two limits separately. And then what is the limit as x approaches 1 of 5x? Well, that part is actually easy, right? Because this one we can just plug in 1. And so this part of the limit is going to be equal to 5. So what we're going to do is we're going to focus on this first part and use the squeeze theorem, and then once we're done, we'll add that 5 in. Okay, so how are we going to tackle this? So again, we want to start by saying, okay, we know that cosine of 1 over x minus 1 has to be between -1 and 1. And then we can multiply both sides with x minus 1 squared, and that will give us our top and bottom function. So if we multiply both sides by x minus 1 squared, we'll get negative x minus 1 squared is less than or equal to, our middle function will now be x minus 1 squared times cosine of 1 over x minus 1. And then we have is less than or equal to just x minus 1 squared. So we found our top and our bottom function. So the next thing we need to do is we need to find the limit of the top and bottom function and confirm that those two limits agree. And if those two limits agree, then we'll be able to conclude that the blue function in the middle has the same limit. So the limit as x approaches 1 of negative x minus 1 squared. So we can just plug in 1, right? And we get negative 0 squared, which is 0. And then we can do the same thing with the top function. So that is x minus 1 squared, and we also get 0. And so from there, we can conclude that the limit as x approaches 1 of x minus 1 squared times cosine of 1 over x minus 1 is equal to 0 as well, because it has been sandwiched between those two. And I'm just going to show you the graph of specifically of this function. So remember we still have to go and add that 5 on, but let's forget about that for a second and just focus on this blue function. So I have that graphed as well in Desmos. So this is what the blue function looks like. So it has a very similar shape to what we saw on the last one. It's just that now it's the squiggle is kind of converging on 1. And that's basically because everything's been shifted to the right by 1 because of this x minus 1. And so similarly, our top and bottom functions have also been shifted to the right. So we still have a parabola on the top and a parabola on the bottom, but they've just been shifted over. And again, we see that our blue graph is getting squeezed between the red and the green graphs. Okay, so now let's finish this problem off. So we want to say that the limit as x approaches 1 of this stuff is going to be equal to, so I'll just rewrite it down here, I guess. So the limit as x approaches 1 of x minus 1 squared times cosine of 1 over x minus 1 plus 5x. So we just figured out that the limit for this first part was equal to 0. And then we earlier said that the limit of the 5x part was equal to 5. And so altogether, our final answer is 5. All right, so that's it for this video. There's not really too much more. Like, all of these squeeze theorem problems are going to be pretty similar, but definitely check out the activity for today, and make sure that you kind of know how to write down all of the steps yourself, and know like what needs to be included in your answer. All right, I will see you in the next video.